3D human motion prediction is an important part of any application that a robot needs to react to the human behavior. It can include a variety of applications from predicting motion of pedestrians in an autonomous vehicle or to design a companion robot for a mall or an elderly living facility. In this work, we have studied the problem of diverse human motion prediction. Predicting human motion sequence can be defined as probabilistic or deterministic approaches. In probabilistic methods, similar to how our brain works, we predict multiple future motion sequences for an observed motion sequence, while in deterministic methods, we output single sequence per observation. Deterministic methods are normally easier to train as we can directly calculate the gradient, but because they are not considering the diversity and multimodality of human behavior, they may not be the best choice for robotics application. Here we attempt to get both benefits by using multi-deterministic generative adversarial networks. Most of the previous work focused on predicting 3D pose relative to the human hip, while we predict both 3D pose and human trajectory. We also show how using 3D pose improves the trajectory forecasting. Given a sequence of human motion, our system generates n diverse human motion. We design it using 3 modules. The first module is the 3D pose estimation module. It gets the human 3D pose and output the future human 3D pose sequences. The second module is the hip prediction module. It estimates the future trajectory of each predicted human 3D pose by receiving the input hip trajectory and their forecasted 3D pose. Using 4 supervised losses, our system increases the diversity and accuracy of the prediction, while it also benefits from unpaired data by using discriminator that learns to distinguish between real and generated sequences. In our experiment, we compare our system versus DILO and SDPOTR. SDPOTR is specifically designed for single human motion forecasting, while DILO is one of the state-of-the-art in diverse 3D pose prediction. In the first experiment, we compare our system using only 3D pose by predicting everything centered at pelvis joint. We did this experiment as DILO is trained this way. Our metrics chosen to both compare the accuracy and diversity of the prediction. The first metric is APD, which is average pairwise distance to calculate the diversity of the samples. Then for accuracy, we have average pairwise distance error and final displacement error. Then the last two are multimodal version of AD and FDE to compare all the prediction with the dataset. Based on this result, our model achieves the highest diversity while it has the lowest error. In the following, we go over 2 qualitative examples for the 3D pose experiment. On the left, we can see the ground truth example, and then first row is our method and the second row is DILO, our baseline. We can see here 10 samples of the prediction for each method. These are our predictions. As it can be seen, they are pretty diverse. We have motions from sitting down, crouching, walking to the left and the right. While for DILO, we have a little bit of less diversity. For instance, we don't have sitting down. Then this is the second example, our method versus DILO. In the second experiment, we evaluate our full model versus the SDPOTR and an adapted version of DILO by adding the hip joint to the joint DILO predicts. Based on this result, our method achieves the highest diversity with lowest error. Also, as an ablation study, we compared 3 different versions of our system. Here we have DMMGAN as our full model, then we have MMGAN, which is our model trained without the diversity loss. Based on the result, if we remove the diversity loss, the samples become similar, which shows the importance of this loss on the diversity metric. Lastly, we have the hip only version, which is our model with only hip prediction module. Here we explore the importance of attention over 3D pose module for predicting trajectory, and the result of hip only module shows the importance of attention as we have an increase in the trajectory error. In the following, we will first go over the qualitative result of 3D motion experiment and then our ablation study. Here on the left, we have the ground truth, and then on the first row, we have DMMGAN, our method, and then we have adapted DILO and SDPOTR on second and third row. On the right side, we will have 10 samples of our model and DILO and 1 sample of SDPOTR. we can see our model result. These results shows a good diversity. Then we have the adopted DLO and STPOTR. For the adopted DLO, we can see the samples become less real or less similar to distribution of normal human behavior, and for STPOTR we can only have one output, as is the deterministic approach. And here is the second sequence. Again, we have the result of our model, then we have our baselines. For our ablation study, we have a similar structure. We have DMMGAN versus MMGAN, which MMGAN is our model without the diversity loss. As it can be seen, the DMMGAN is pretty diverse, while for MMGAN, everything is stationary. Thank you for your attention.